Hey class, this is Mrs. Ulrich again. Alright, we've got to do 2 slides a minute, so here goes. Molecules. Molecules are made up of atoms, so atoms are the building blocks, and atoms can come together to form molecules. Those molecules are larger than the atoms, of course, right, because they're made up of atoms, but they're still too small to be seen with normal microscopes due to them being smaller than the wavelength of visible light. Molecules are that smallest particle that has two or more atoms that share electrons, like water. Hydrogen and oxygen come together. You have two hydrogens, one oxygen. They come together and you get a water molecule. Smallest one, so I couldn't break it up into one hydrogen and one oxygen. It has to be two hydrogen and one oxygen, and that makes a molecule. So matter is usually made of molecules, if it's a gas or liquid at room temperature. And matter that is made of molecules could have a whole bunch of the same kind, or it could be a mixture of different molecules. So like water is almost entirely H2O molecules, but air is oxygen molecules and carbon dioxide molecules and all of those different types of molecules. So it's not just one kind. Here's some models of some molecules. So you have an O2 oxygen molecule, an NH3 ammonia molecule, and a CH4 methane molecule. So you can kind of see how this is structured. It's actually a structure, it looks somewhat like this, with these four branching off, or the three branching off, and the nitrogen in the middle, or the carbon in the middle. So they're bonded in a defined way. What are molecules made of? They are made of atoms. Right, compounds, they have properties that are different from the properties of the elements that are made up of them. So they're made up of atoms of different elements in a fixed proportion. So it's like, well, I have two of this and one of this, fixed proportion. The chemical formula tells us the proportion. So for example, carbon dioxide has one carbon and two oxygen. So for every carbon atom, we have two oxygen atoms. That is a compound. Water, H2O, table salt, NaCl, and carbon dioxide are all compounds. Air, wood, and water are not compounds, or salty water, because the proportions of their atoms vary. So they're not a strict proportion. A compound may or may not be molecules. It doesn't have to be a molecule to be a compound. Water and carbon dioxide, H2O and CO2, are molecules, but salt, NaCl, is made of different kind of atoms in a regular pattern. So you'll see here, every chlorine atom, this green one, is surrounded by 6 sodium atoms. So it's totally surrounded by sodium. And every sodium is surrounded by 6 chlorine. 1, 2, 3, 4, so on and so forth. So it's a repeating pattern, and if you looked at the whole thing, it would continue to repeat, but there's not one molecule in here. Alright, the mass of an atom is primarily concentrated in the nucleus. So an atom has a nucleus, which is in the core of it. It's mostly empty space, and almost all of its mass is packed into the nucleus in the middle. That was demonstrated in what was Ernest Rutherford's gold foil experiment. Hugely famous experiment. And here's what it was. He had a beam of alpha particles, shot them at some gold foil, and a lot of the alpha particles went through, but quite a few also got bounced back. See here how they're kind of getting bounced back? What happened is they were repulsed by the nuclei because these alpha particles are positively charged and the nucleus is positively charged. And so those positive charges repelled one another and it got pushed back. Whereas the rest of them just went zipping straight through. Nothing repelled them. So that's how we discovered the nuclei at the centers. He said, well, if it's getting hit back, there must be something there that's pushing it back. Alright, Rutherford decided it had to be positively charged because it's repelling those positively charged alpha particles. It had to be very small, right, so he realized the atom must be empty space. But it also has to be massive enough, big enough, that when those big ol' alpha particles hit the nucleus, that the nuclei don't just go running away. So he found the nucleus. But, like we said, the atom is mostly empty space, so the nucleus occupies less than a trillionth of the volume of an atom. Atoms' nuclei are super compact and super dense because all of the mass of an atom is in the nucleus. Electrons count for almost nothing. So if you took just the nuclei, you got rid of the electrons, you just took the nuclei, put them into a little 1 centimeter lump, so a little tiny little lump, it would weigh 1 billion tons. That is how dense nuclei are. Obviously you can't do that because the nuclei repulse each other because they're positively charged and like repels like. Under special circumstances with lots of energy, you can smash things together and get fusion. Super high energy process. Alright, the principal building blocks of the nucleus are our nucleons. Those are neutrons and protons. They're called nucleons because they are in the nucleus. Neutrons are neutral, they have no charge, and protons are positive. They have a positive charge. Atoms are different from one another by the number of protons. So hydrogen has 1 proton, helium has 2 protons, so on and so forth. Their atomic number relates to their number of protons. And if you have a different number of protons, you now have a different element. Atoms that have the same number of protons are the same element. You cannot have 6 protons and be something, and have 2 things with 6 protons and have them be different things. That cannot happen. Also, they have electrons that orbit the nucleus. You can see in this diagram here, as they go around, these are the electrons that orbit the nucleus, or surround it in a cloud, more like it. And those are negatively charged particles. So neutrons, neutral, protons, positive, electrons, negative. Alright, then there's something called an isotope. That is when the number of neutrons vary. There are different numbers of neutrons. So when you have the same element, so same number of protons, but a different number of neutrons, that is an isotope. Same element, different number of neutrons. For example, hydrogen has a single proton. So when you add a neutron, you get something called deuterium. That's an isotope of hydrogen because it has a different number of neutrons. If you put in 2 neutrons with that single proton, then you get tritium. And there are lots and lots of isotopes for lots of different elements. Every element has a variety, it's just a matter of if it's common or not. Typically speaking, those isotopes are not as stable as the normal occurrence of that element. Also, as you go along, you'll find that the lighter elements, atomic number 7, somewhere in there, will have 7 protons and 7 neutrons. But when you get up to, the 88th element, it's going to have 88 protons and, about 100 neutrons. So a lot more neutrons than protons as you get heavier. So atoms are classified by their atomic number. That's the number of protons in the nucleus. Hydrogen has 1 proton, so its atomic number is 1. Helium, 2, so it's 2. You can see on the periodic table in our classroom. Lithium has 3, so its atomic number is 3, right? Okay, atomic number is not the number of neutrons. It is not the number of electrons. It is only the number of protons. Therefore, if 2 things have the same atomic number, they are the same element. Because if 2 things have the same number of protons, they are the same element. Also, within that, we have neutrons are neutral, protons positive, and electrons are negative. And like charges repel each other, but opposites attract. Right? So protons don't like other protons, but they do like electrons, because their positive charge attracts the negative charge. Opposites attract. And electrons attract protons. There's something called the strong nuclear force. It's super strong, but only across short distances. So it's not going to, pull you to your desk with the strong nuclear force. It's a really short distance. So where's the mass of an atom concentrated? In the nucleus. Alright, electrons in the atom. The arrangement of electrons in the shells about the nucleus dictates the atom's chemical properties. So the way that its electrons are arranged gives us the chemical properties of an atom. Electrons are super tiny, right? All the mass is in the protons and neutrons. Electrons pretty much, we imagine that they don't have a mass, even though they technically do. Neutral atom, charge of 0, number of protons is the same as the number of electrons. They balance each other out. 3 positive, 3 negative gives you 0. If the protons are not equal to the number of electrons, then you get a net charge, some overall charge, either, +1, a -1, +2, a -2. The charge isn't 0. That is called an ion. An ion is a charged particle. There are two ways of bonding them. One, they can be held together by sharing electrons. That's a covalent bond. So that actually wouldn't be an ion. They would just be friends. And then atoms stick to each other when ions are formed, and those ions are held together by electric forces. That's an ionic bond. So an ionic bond, you take two charged particles and stick them together. A covalent bond is different. Things stick together for other reasons. They share electrons. All right, so then there's this model of the shell model of the atom. So you have different shells around the nucleus, and in each shell you can hold 2, 6, 10, 14 electrons, whatever it is. So it's kind of like planets orbiting a sun. In reality, though, the electrons are actually in a cloud surrounding it and don't have a particular path, but we model them as having specific paths. Finally, the periodic table. It's that chart, the big old chart painted on the wall, lists atoms by their atomic number and by their electron arrangements. So, you read left to right, each element has one more proton and one more electron than the preceding element. The extra electron is to balance out that positive charge. And as you move down, each element has one more shell filled to its capacity than the element above. So you add a shell each time you go down a row. Here's your periodic table. The atomic number, the one at the top, the little one at the top, is equal to the number of protons, and the number below is the atomic mass. So if you looked in your textbook, you would see the atomic mass. Each row in the periodic table has a different number of shells of electrons, and vertically they're arranged on their basis of the similarity of the outside electrons, how those are arranged. So if you were to learn about electron configurations like you do in chemistry, you can use the periodic table to help you figure that out. Elements that are in the same column are in a group or family of elements. And elements in a group have similar chemical properties because their electrons are arranged similarly, right? And the electrons dictate the chemical properties. Those properties are things like melting and freezing, electrical conductivity, taste, texture, appearance, color, or how it reacts with other things. So what does the arrangement of electrons determine? The chemical properties. Matter exists in 4 phases. All right, this is your introduction to the next 3 chapters, 1 for this semester and 2 for next semester. Matter exists in 4 phases: solid, liquid, gaseous, and plasma. We won't really talk about plasma. We'll talk about solid, liquid, and gas. So solid phase, everything's in motion. Okay, when things stop moving, the world is over. If we reach absolute 0, everything is dead, the world is done. Right? So everything is constantly moving. Even if it doesn't look like it is, it is. So in the solid phase, everything vibrates. In the liquid phase, that vibration has more energy, so they shake apart and move around more. In the gaseous phase, they have even more energy, so they zoom all around the place. And in the plasma phase, there's so much energy that those ions or molecules or whatever break apart, and you kind of just have electrons and ions working with each other, so they're not really separate things. Finally, all substances can be transformed. Water is ice. Heat the ice, it turns into water. Then heat that, turns into steam, and then heat that, and you'll get a plasma. So what are our 4 phases? Solid, liquid, gas, and plasma. Go read your textbook.